Okay, let's jump right into this explainer. Welcome to our holographic training simulation. Today, we're going to translate the dense, invisible mechanics of fluids into dynamic, highly visible neon vectors. We're unpacking the fundamental physics of fluids, and it's going to be a fun ride.
Here is our digital roadmap for the simulation. First, defining fluids and pressure. Second, hydrostatic pressure and measurement. Third, Pascal's principle and hydraulics. Fourth, Archimedes' principle and buoyancy. Fifth, the equation of continuity. And finally, number 6, Bernoulli's equation. Let's get started.
Section 1, Defining Fluids and Pressure, the absolute basics of our simulation.
So, what exactly is a fluid? It seems like such a simple, everyday question, right? But in physics, we need a highly specific, airtight definition before we can even think about calculating flow rates or energy transformations. We aren't just talking about a glass of water here. We're literally defining an entire mechanical state of matter. Fluids, and that means whether they're totally incompressible liquids or highly compressible gases like the oxygen we're breathing right now, are fundamentally defined by their inability to withstand shearing stress. Think about it. If you try to push the top layer of a fluid sideways, it doesn't fight back and resist like a solid block of wood would, it just flows. Because of this totally unique property, it's way more useful to measure fluids using density and pressure rather than the standard mass and force equations we'd use for solid objects. Moving on to Section 2, Hydrostatic Pressure and Measurements. Let's look at fluids at rest. Okay, look at this massive number projected here, 1.1 times 10 to the 8th power pascals. That is the staggering hydrostatic pressure at the very bottom of the deepest ocean trench. It's a truly dramatic scale of fluid force just crushing down from above. As any scuba diver knows, pressure increases with depth. Why? Because the pressure at any point in a resting fluid is due to the actual physical weight of the fluid stacked directly above it, pressing down. Now, the crucial point we need to separate here involves two key concepts: absolute pressure versus gauge pressure. Absolute pressure accounts for the total weight bearing down on you, meaning the fluid itself, plus the roughly 110 cans of Pepsi worth of atmospheric weight resting squarely on your head at sea level. Gauge pressure, on the other hand, is just the difference between absolute pressure and atmospheric pressure. It isolates and measures only what the fluid itself is adding to the mix. To actually read these invisible crushing forces, engineers use some really clever analog tools that rely entirely on the static balance of liquid densities. A mercury barometer measures absolute atmospheric pressure, while an open tube manometer measures the gauge pressure of a gas confined in a tank. Both of these ingeniously rely on one golden rule. In static equilibrium, the pressure is exactly the same for all points at the exact same horizontal fluid level. Section 3, Pascal's principle and hydraulics. Let's see how we can magnify some force. Pascal's principle is absolutely brilliant. It states that if you change the pressure of an enclosed incompressible fluid, that change transmits undiminished everywhere inside that fluid. This perfectly explains why, when you squeeze the bottom of a toothpaste tube, the paste predictably shoots right out the top. The pressure doesn't fade out, it travels flawlessly through the entire enclosed liquid. And taking that a step further, notice how these pressure vectors map out the way Pascal's principle allows a tiny input force to literally lift heavy machinery, like a car. Because the pressure change is equal everywhere, a small force pushing down on a small piston area creates the exact same pressure against a much larger output piston, massively magnifying the output force. It's almost like magic. But the catch, the trade-off, is just that the larger piston moves a much smaller distance. Section 4, Archimedes' principle and buoyancy. Exploring the upward push. This classic realization by Archimedes is a real game changer. It reveals that buoyancy is entirely dictated by the mass of the fluid pushed out of the way. Any object completely or even just partially submerged experiences an upward buoyant force that is perfectly, exactly equal to the weight of the fluid it displaces. And if you check out this breakdown, notice how the net force dictates apparent weight underwater. Even for a sinking stone where gravity is clearly winning, that upward buoyant force literally subtracts from the object's actual weight, creating a much lighter apparent weight. And for a perfectly floating water sack, well, the buoyant force perfectly balances gravity, meaning its apparent weight is exactly 0. All right, Section 5, the equation of continuity. It's time to set these fluids in motion. Now, real fluid dynamics in the physical world are incredibly messy and complex. So before we unleash the math in our simulation, we really have to lock in 4 specific ideal fluid parameters. We're going to assume the flow is perfectly steady, the fluid is totally incompressible,
It's non-viscous, meaning zero internal friction, and it is irrotational, which basically just means the fluid particles aren't tumbling and spinning as they move forward.
It is vital we distinguish between these two flow states. Laminar flow is smooth, gentle, and highly predictable. Turbulent flow, on the other hand, is completely chaotic. Our upcoming continuity equations, they only function flawlessly within a steady, laminar environment where the velocity at any given point doesn't suddenly change as the clock ticks.
This transition is brilliantly illustrated right here. Watch how the smooth, predictable base of the smoke suddenly fractures into wild, unpredictable turbulence the moment it accelerates. That fracture point, that's the exact critical speed threshold where our nice, neat, ideal mathematical models would have to be thrown out and swapped for much more intense, complex formulas.
But sticking to the ideal, look at the neon vectors tracing the fluid's path around the cylinder without ever crisscrossing or intersecting. This is a flawless visual of an ideal fluid in motion. We actually call these paths streamlines, because two streamlines can literally never intersect. If they did, a single particle would have to somehow travel at two different velocities at the exact same time, which is impossible. We can use them to define a tube of flow. The equation of continuity gives us the mathematical guarantee that within this tube, the volume of fluid flowing in per second must exactly equal the volume flowing out per second. Meaning, if the tube narrows, the fluid has absolutely no choice but to speed up. And finally, Section 6, Bernoulli's equation, which is all about energy conservation in moving fluids. When you break it down step by step, Bernoulli's equation is really just a fluid-specific reformulation of energy conservation. You take the kinetic energy density, you add the gravitational potential energy density, and then you add the fluid pressure. The mind-blowing result is that this total sum will always remain perfectly constant along a streamline. If one of those factors goes up, another absolutely must mathematically decrease to balance the scales. So the absolutely crucial takeaway from all these high-tech equations is this highly counterintuitive reality. Faster-moving horizontal fluids actually exert less pressure. The energy literally shifts from pressure directly into kinetic speed. Pretty wild, right?
As we power down the simulation today, I want to leave you with the final thought. If these mechanical fluid equations flawlessly govern everything from the literal blood pumping through your arteries to the hydraulic systems landing a massive 400-ton jet plane, what unseen hydrostatic pressures and flow rates are silently acting on you right now at this very moment? These invisible, perfectly balanced forces shape absolutely every physical movement in the world around us. Thanks for joining me in this explainer, and we will see you in the next simulation.